Hello all, welcome to this course on time series modeling and forecasting using R. Now again, if you vaguely remember, if you are following this week, we are talking about spectral density function, Fourier transformation. So the focus idea for this week has been transitioning from a time based approach to a frequency based approach. Okay. Now just in the last lecture, if you remember, we studied entirely about the spectral density function, or in short SDF, some of its properties, some implications of SDF, and towards the end of last lecture we talked about a few examples. So white noise, AR1, MAQ, and then random walk, and for each of those examples we laid down the expression for the underlying SDF. Okay. So now in today's lecture, before we start with anything new, I will start today's lecture by mentioning a few practical applications of spectral analysis in general. Okay. So we will start with signal processing. So the first one is signal processing. So spectral analysis is fundamental in signal processing for understanding and manipulating signals in a frequency domain. Okay. So the underlying few examples are as follows. So noise filtering. So let's say the first application could be identify and remove noise from a signal by filtering out high frequency components using the SDF. Right. Now let me just take a pause here and try to explain the first example, because there has to be some practical component also, right. I mean, simply studying theory won't help. So how do you connect theory and then to applications or to practice is kind of the important part. Okay. For example, again if you reread this example, so identify and remove noise from a signal by filtering out some of the high frequency components using the SDF. So again if you remember a couple of pointers from the last section, that and where we discussed that I can actually chart out the SDF, isn't it, because I can chart it out or I can graph out the path of the underlying spectral density function. And if you remember vaguely that wherever you see peaks there, so wherever you see peaks in the underlying SDF, so these peaks correspond to significant frequencies. So the underlying significant frequencies are these and these. Okay. So hence once you chart out the SDF, once you create the SDF, once you graph out the SDF, so wherever you see peaks in the underlying SDF, you kind of can immediately say that which frequencies are significant. Okay. And once you identify such frequencies, one can actually filter them out, or one can identify and remove noise from a signal by filtering out some of the high frequency components using the SDF. Because what might happen is that if you are transmitting a signal and all these peaks or all these high frequencies or wherever you have peaks in the SDF could mean noise. So think of a situation where you are listening to some radio, right, and while listening to some song on the radio or some news on the radio, suddenly you might have witnessed that there is some disturbance, right, and then wherever you see you have disturbance in that transmission, then there is some extra noise there, right. So you have some extra hush there, or you have some extra blast, whatever, right. So all these are noise components, and one might want to remove all the noise components. So wherever you see some increased activity of frequencies, you want to filter them out. Hopefully the idea is clear. So and then here the spectral analysis comes to rescue. So this is exactly my second example. So cleaning audio recordings or improving image clarity. So again, if you have any audio recording and suddenly you see a spike there, that spike could mean some noise. So noise means some extra volume suddenly, something like that, right. So all such noise components are unwanted and you want to filter them out. Okay. So both these examples come under the heading of noise filtering. So the first application is signal processing. There could be another application in telecommunication. So the idea about modulation and demodulation. So the first example is that spectral techniques analyze and design communication signals, let's say AM, FM or digital modulation, etc. And what could be one of the examples there? So ensuring that transmitted signals occupy specific frequency bands only. So you are sort of restricting all the transmitted signals to particular or a few bands there. Okay. Then the third example could be entirely different, coming from finance and economics area. So let's say spectral analysis could be used to detect periodic patterns, trends and cycles in financial and economic time series. Okay. A couple of other examples within that area is that market cycle detection. So let's say identifying cycles in stock prices, interest rates or GDP growth rates, etc. And what could be one of the examples there? So using spectral density to uncover business cycles or seasonal patterns. Okay. So this is a particular example which is not coming from signal processing, so slightly different area which is again of very much relevance. Okay. And probably one last area could be, let's say, medicine and biology. So how does spectral analysis comes into play there? So, the spectral analysis is crucial in analyzing some biomedical signals. For example, ECG, right, or electrocardiography signals or ECG signals, which are sort of helpful to detect abnormalities in heart rhythms, right, by identifying irregular frequencies. So, the heartbeats could be irregular, right, and this is a problem, right. So, the example could be diagnosing arrhythmia. So, arrhythmia means irregular heartbeats, right, and then irregular. So, heartbeat is nothing but the heart is transmitting some signals, right. So, can't you put forward a model which is coming from a frequency domain, so identifying the frequencies, right, and then filtering out some unwanted frequencies, trying to make it smooth, right. So, diagnosing arrhythmia is one application in medicine and biology. So, hopefully now you have the motivation as to why does one have to transition even from a time based modeling to a frequency based modeling. Okay, so now the key idea in today's lecture would be spectral density estimation. Okay, so once you formulate SDF, once you formulate the underlying model containing all the unknown parameters, so then the idea remains is that how do you estimate the underlying parameters in the SDF. Okay, so here we will broadly talk about the spectral density estimation in general. Okay, so here we will break it down into two parts. So, the first part is parametric estimation. So, parametric estimation means wherever you have some unknown parameters into play and probably you might know the underlying distribution as well. Okay. So, in general parametric estimation in statistic means that so if you are able to put forward some statistical distribution, then it is called as parametric estimation. And on the other hand, if you are not able to put forward or conclude that what distribution it should follow, then we have a idea called as non-parametric estimation. Okay. So, here we will clearly break it down into two parts. So, parametric estimation and then non-parametric estimation. The first one is parametric. So, parametric methods assume a specific model for the time series. So, as discussed a short while back, that if you happen to know the underlying model or if you can sort of put forward a specific model for the time series, one can actually use the parametric umbrella of estimation. Okay. So, what do you mean by modeling? So, the models could be as basic as let us say ARMA, ARIMA, etc. Okay. Again, so parametric methods assume a specific model for the time series such as ARMA, ARIMA, etc. and estimate the parameters of that model to compute the spectral density. So, if you are able to put forward let us say either ARMA or ARIMA as a model on the time series, then we want to estimate the underlying parameters of the ARMA model on the underlying parameters of the ARIMA process, etc. And again probably many of you might know that or should know rather that what are the parameters in the ARMA model. So, of course, the phi coefficients and the theta coefficients, okay, and probably the sigma square which is variance of the error component. Similarly, ARIMA, what are the parameters? Same. So, all the phi coefficients, all the theta coefficients and probably sigma square which is variance of that Et or epsilon t basically. Okay. So, what are the steps here? So, the first step is model selection. So, of course, we have to select or choose a particular or appropriate model. Okay. So, choose a model class, let us say ARP or MAQ or let us say ARMA PQ based on the characteristics of the time series. Okay. So, the first idea or the first point under the steps is model selection. So, choose a model class such as ARP, MAQ or ARMA PQ based on the characteristics of the time series. Second is parameter estimation. So, estimate both the parameters let us say phi and theta of the chosen model using usual methods like MLE, etc. So, wherever possible one can apply MLE or one can actually apply method of moments also, right. So, whichever applicable methods are there for parameter estimation of that particular model, one can actually apply. So, a more general looking method is rather MLE, right. So, let us say, so the first step is model selection. So, let us say you choose ARMA PQ model and now the second step is parameter estimation. So, you want to estimate all the underlying coefficients. So, all the phi coefficients, all the theta coefficients using appropriate techniques, let us say MLE. Okay. Then the last component or the last step is compute the spectral density function. So, once you formulate a model, once you estimate the model completely, then I can actually write down the SDF. So, use the analytical formula to compute the SDF of the chosen model. Okay. Make sense? So, what exactly are the pros? So, some of the pros are it provides some smooth estimates, right. So, parametric estimation, so the pros of parametric estimation is that it provides smooth estimates. And second advantage is that it is suitable for well modeled stationary processes. So wherever if you know the actual model, let's say ARMA PQ, ARIMA PDQ, AR, MA, SARIMA, etc. So whenever a particular complete model is defined or rather well defined, there exactly you can use a parametric estimation technique, right? Because if you know the model, if you are able to estimate the model using MLE or method of moments, then why should you go ahead with non-parametric, right? So there parametric estimation is suitable for well modeled stationary processes. But at the same time, there are some disadvantages as well, or what exactly are the cons. So requires the correct model specification, right? So the second advantage here could be a disadvantage also, that it has to rely on some well modeled stationary process. So the correct model specification should be known. If it is unknown, then of course you can't move ahead with the parametric estimation, or if you are not very clear about, let us say, what the model could be or what the model would be, then parametric estimation is not the solution. And second con or the second disadvantage is that it may not work very well for complex or unknown processes. So the overall time series behavior is complex, or the overall time series behavior is unknown, right? Or you have a combination of different, let's say, two different time series, something like that. So where the overall structure is slightly complex, there parametric estimation might not be the solution. Okay. So hopefully the first set of estimation is clear, that parametric means that some underlying model is known to you and you are able to estimate the parameters of that underlying model using MLE, method of moments, etc. Right, and once you estimate the model, the last step is to create that HDF from the analytical formula. Now exactly on the other hand, we will talk briefly about non-parametric estimation. So non-parametric methods do not assume, so as discussed earlier, non-parametric approaches do not assume a specific model for the time series and directly estimate the HDF or the spectral density from the data itself. So here we are not saying that the underlying model is ARMA or ARIMA, nothing like that, okay, and hence we have a non-parametric approach. Okay. Now we have a very famous approach underlying the under the non-parametric framework, which is called as a periodogram. Okay. And of course, in almost any famous textbooks on time series or spectral analysis, you will find the idea about a periodogram. So what exactly is a periodogram? So a periodogram is nothing but a fundamental non-parametric method for estimating the HDF or the spectral density function. So one can actually estimate the HDF through a periodogram. Okay. And a periodogram, it provides a measure of the power. So power is nothing but variance. So power of a signal, when you say a power of a signal, so power of a signal is nothing but the variance of a signal. Okay. So a periodogram provides a measure of the power or variance of a signal at different frequencies. Now again, I can graph a periodogram. So periodogram is nothing but a graph, by the way, which sort of involves the significant frequencies and what is the variance of the underlying signal at those significant frequencies. So don't worry, we will see some examples down the line where we will see some periodograms, and obviously in the R session towards the end we will tie all these details and then sort of put forward a common practical approach there. Okay. But again, like I said, I can actually graph or I can chart out a periodogram. So periodogram can be graphed out, and in that graph one can actually identify the significant frequencies of the signal having some different powers. Okay. Okay, but then entering into small technicalities, so I can actually define periodogram. Okay, so how do you define periodogram? So let's say for any discrete time series yt of length capital T, okay, so yt is assumed to be a discrete time series of length capital T. The periodogram at frequency omega is defined as follows. And exactly how? So I omega is nothing but 1 by capital T absolute value of summation t going from 1 to capital T yt into e to the power minus I omega t and then whole square. So in a way all the formulas are kind of slightly similar, right. So even from the earlier lecture, the last lecture, we defined S omega, right. So even there the S omega formula involved some summation, some integrals, and then this component was there. So e to the power minus I omega h, and then here we have t. So you have slight difference between formulas for S omega, I omega. Now again here the whole difference is, it's not 1 by 2 pi, but rather 1 by capital T. So capital T is what? The length of the time series, right. And then again you have some absolute value summation running from 1 to capital T unlike minus infinity to infinity there, right. So, all these are some subtle differences, but my point is that this component that you see here almost appears in all the formulas. So, e to the power minus I omega into something. Okay. Anyway, so this is the formula for getting the periodogram, which is denoted by capital I of omega, where again, so hence I am mentioning that all the notations are as before. So, omega is a frequency, small t is nothing but time point, capital T is a length, right, and yt is the underlying time series. Alternatively, I can write down the formula of a periodogram slightly differently. So, I omega could be written down in this manner as well. And how? So, 1 by capital T into real part square plus imaginary part square. So, what I am doing here is that since again this formula involves this exponent here or exponential term, and as seen before, you have a relation between this exponential term and sine function and the cosine function. Okay. So, can't I split that into, let us say, the real part and the imaginary part? The answer is yes. Okay. So, I of omega is 1 by t square of the real part plus square of the imaginary part, where the square of the real part is nothing but summation yt into cos of omega t, and square of the imaginary part is summation yt into sine of omega t. By the way, all these things could be easily proved if somebody is really good in mathematics or in general let us say real analysis or complex analysis rather. So, he or she should know the relationship between this guy and then sine and cosine in some sense. Okay. So, in general you have these two kind of alternative formulas for defining the periodogram at a particular frequency omega. Okay. Now, again one important point to note here is that beat s omega, beat I omega. So, again just for a second let me go back to SDF, right. So, s omega denotes the spectral density function. So, this is nothing but a function in terms of frequency. Can you see that? Because omega is a frequency, right. Okay. So, the spectral density function is nothing but a function on the frequencies. So, again if you graph out the SDF or if you graph out the periodogram, on the x axis you will have the frequency always. So, be it a graph of s omega or be it a graph of I omega, makes sense, because both are functions of omega in a way. Okay, I think this important but small point I missed in the last lecture, that both SDF, the spectral density function, as well as the periodogram are nothing but functions of the underlying frequency. Make sense? Okay, so now what exactly are some properties of the underlying periodogram? So, the first property is frequency range. Okay. So, which means that the periodogram is evaluated at discrete frequencies. So, let us say omega k, and then omega k equals 2 pi into k divided by capital T, and of course, k can range from 0, 1, 2, 3, 4 up to t minus 1. So, of course, k cannot be t because t is the last threshold, because t is the number of, because small t goes from 0 to capital T, right. So, k can't be t and k can't go beyond t. So, you have a limitation with k. So, it can run from 0, 1, 2, 3, 4 up to t minus 1, but the periodogram is evaluated at discrete frequencies. So, for each and every frequency, if you replace the values of k 1 by 1 here, I can actually evaluate the periodogram at those frequencies, which are omega k. And second point is, for real value time series, the periodogram is symmetric. Okay. So, for a real value time series, periodogram is symmetric. So, I can actually restrict my frequency range to only 0 to pi rather than 0 to 2 pi, because if you have any real value time series, which in general we have, right, because all the time point, all the values in yt would be real valued, right. You will not have any complex observation, right. So, let us say temperature data, rainfall data, stock price data. So, all these values are real valued. Okay. So, in that sense, for any real value time series, the periodogram is symmetric. So, we can actually restrict the frequency range between 0 to pi only. Make sense? So, these are some underlying properties of I omega or the periodogram. Then the units. So, the second idea is units, again under the properties heading. So, what do you mean by units? So, the periodogram is measured in units of variance per unit frequency. Again, just to repeat. So, the underlying units as to how one measures the periodogram is nothing but variance per unit frequency. For example, if the underlying time series is in volts, then the periodogram is measured in volts square per hertz. So, Hz stands for hertz. Okay. So, volts square per hertz. And then the next one is bias and variance. So, what do you mean by that? So, first one is, the first idea is bias. So, the periodogram is asymptotically unbiased. This is again one very important property that, so firstly, what do you mean by asymptotically? Asymptotically means if something converges to infinity, or on the long run what happens, or in the long run what happens. Okay. So, the periodogram is asymptotically unbiased, which means that expectation of I omega is close to S omega. Okay. So, expectation of I omega is close to S omega. Again, if you sort of forgot that what we are trying to study here is estimation of S omega, right. So, we began this session by so again if you go back a few slides, you will see that we had a heading here which said spectral density estimation. Okay. So, I omega is nothing but an estimate of S omega, isn't it? So, we are trying to estimate that spectral density using a periodogram. Okay. So, in short, the expected value of the periodogram is close to S omega. So, here I am not writing exactly equal to, because it is asymptotically unbiased and not exactly unbiased. Make sense hopefully. So, expectation of the periodogram should be somewhat close to my SDF. And lastly, variance. So, the periodogram is not consistent. This is one drawback probably, that the periodogram is not consistent. So, what do you mean by consistency? Consistency means that the variance does not decrease with increasing capital T. So, even if you collect more and more observations in the time series, so if you go on increasing my capital T, still in that case the overall variance does not converge to 0, or the variance does not decrease, okay, which is probably a disadvantage, because we would want the variance to converge to 0, right. If you collect more observations, then naturally the variance should go to 0, which is not happening here. So, the periodogram is not consistent, but at the same time it is asymptotically unbiased. Okay, so now we will pay attention to what exactly are the steps to compute the periodogram. So, now that we have some idea about what you mean by periodogram. So, periodogram is nothing but an estimate of the SDF, okay, but how do you compute it? So, the first step is transform to the frequency domain, and here we will make use of the DFT, or the discrete Fourier transform, or discrete Fourier representation of the time series. Now, again probably for this you might have to revisit the first lecture of this week, where we talked about Fourier transform, inverse Fourier transform, all these things. Okay. But here transforming to the frequency domain uses the DFT, or the discrete Fourier transform of the underlying time series. So, y and then omega k happens to be equal to summation t going from 1 to capital T y t into e to the power minus I omega k t. Okay. Then the next step is one has to compute the power spectrum. So, there is something called as a power spectrum. Now, what do you mean by that? So, it means that the periodogram is the nothing but the squared magnitude of the DFT scaled by 1 by t. Okay. Again, the periodogram is nothing but the squared magnitude of the DFT scaled by 1 by t. Now, one small typo here is that this should be again y of omega k, and then this y of omega k is the same thing as this thing here. Okay. So, the first step is you find out DFT of a time series, then you somehow square the DFT, scale it down by capital T, and you can get the periodogram at that frequency. Hopefully, this is clear. Again, just to repeat, first step is find out the DFT of the time series using this structure here. Okay. And then once you find out y of omega k, you square it and then scale it by 1 by t, and then you get I of omega k. Okay. And then the third step is frequency resolution. So, what do you mean by that? So, the resolution of the periodogram depends on the length capital T of the time series, and in turn what do you mean by that? So, longer capital T or longer T provides better frequency resolution. Okay. And here we have a small relationship. So, triangle f, so this is a technical notation. So, triangle f equals 1 by capital T triangle T. So, triangle f means very small time step or a very small interval. So, by the way, this notation is called as a sampling interval. So, what happens in a very small time span? Okay. So, triangle f equals 1 by capital T into triangle T. So, by the way, this step is kind of a technical step. If you do not want to pay much attention here, you can sort of ignore this, but this is one step to compute the periodogram, which is called as a frequency resolution. So, once you sort of formulate the DFT, then once you sort of connect the DFT to find out periodogram, last step is to sort of do the frequency resolution. right. Okay, so once we understand that what do you mean by periodogram and then how do you get the periodogram. So what are the limitations now? So some limitations of the periodogram. First limitation is a noisy estimates. So the variance of I omega does not decrease with sample size t. We've seen this earlier. So I omega is not consistent, leading to noisy and unstable estimates. So even in the long run, since the variance is not approaching 0 or variance is not reducing, we might observe some noisy estimates down the line. Second is spectral leakage. So what do you mean by that? So when the time series contains frequencies not aligned with the discrete Fourier frequencies, power leaks into adjacent frequencies. There might be a case that since you are trying to estimate S omega using I omega, but the underlying S omega, the frequencies in S omega and the frequencies in I omega may not match exactly. So in that case what happens is there is some spectral leakage. So there might be some leakage or power leaks into the adjacent frequencies. Okay. Hopefully this is clear that if both the graphs of S omega and I omega are not superimposing, so let us say if you have, this is the graph of S omega, something like that, and then let us say on top of that I am superimposing the graph of I omega, and then here in I omega I can see that the peaks are slightly different. Okay. So there could be a situation where you have some spectral leakage. So the power leaks into the adjacent frequencies. And lastly, resolution versus variance trade-off. So high frequency resolution comes at the cost of increased variance and vice versa. So if one needs some high frequency resolution, so let us say image clarity or signals or the pixels in an image, right, and if you want some high frequency resolution, that always comes at a cost of increased variance and vice versa. So if you want some high frequency resolution, if you want some immaculate resolution, then the variance also increases. So you have a trade-off. So between resolution and the variance. So hopefully in this lecture I have tried to cover a few ideas about periodogram, and periodogram is one very useful, very important method of estimating the underlying spectral density. So for that matter, down the line if you have any practical data set that you want to sort of put forward a frequency domain based time series approach on that, trying to put forward a model, and during that procedure you would want to find out the SDF, right, because spectral density as seen in the last lecture is a key to this entire process of the frequency domain based approach. Then how do you estimate SDF? So the periodogram is one such estimator which is non-parametric, you do not require any modeling here of the underlying SDF. Now in the last lecture of this week, last theoretical lecture of this week, we will try to close the idea about spectral density, periodogram, spectral representation by some final points. Okay. Thank you.